Well, we're starting a brand new chapter today. This is chapter 7.1. We're looking at exponential growth, decay, and logarithms in this chapter. This section is on exponential growth functions. All right, so this is the next parent function that we're going to add to our list. So you may want to dig out your cheat sheet, your semester final cheat sheet, and get this formula on your sheet as well. The exponential growth function, parent function, is right here. Y equals a times b to the x. When we put in all of the a, h, and k values, just like we do in any of our vertex form type equations, it looks like this. Y equals a times b raised to the x minus h plus k. When we do our shifting, we're going to do our shifting in the same order that we've been doing all the rest of our shifts. We're going to look inside here first and deal with the x coordinate. Whatever it says next to the x, you do the opposite of what it says. Then you're going to change the y value. First thing we'll do is look for a multiplier in the front. We'll take our y coordinate times that multiplier. And then the third thing we do is add in the k value to our y number. That will give us our new spots. So first we need to have some go-to points for this graph. Our go-to points for the exponential curve are always going to be 0, 1. Always 0, 1. And the second point we're going to use, just 2 points for our go-to points for this one. Second point is going to be 1 comma b. And the b value is going to change every time depending on what we've got in our particular equation. So the b value, if you want to look for what are you going to use for that b value, follow the arrow. B value is this number right here. That's what we're going to use as our second go-to point value. Domain for the exponential growth function is all real numbers. Eventually, if you follow this blue curve right here, eventually you will pick up every single x value. It's the range that has limitations. And when you look at the parent function, the range is only above the x-axis, which means that your range is going to be all values greater than 0, not greater than or equal to. It is not going to touch this bottom line down here. It's going to get extremely close. So now we bring in a brand new word. This is a vocab word you want to write down for sure. This is called an asymptote line. Asymptote line is known as the line that your curve comes close to but does not touch. And that asymptote line is the k value from the back of your equation. So if you follow the little purple graph here, the k value number in the back will represent the dotted line, asymptote line, that we will draw in on our graph. All right, let's look at a couple samples here. First one, y equals 2 to the x. This is about as basic as you can get. There is no a number in the front, there is no number up here with x, and there is no k number sitting in the back. So this is just y equals 2 to the x. My go-to points, 0, 1, all the time, 0, 1. And the second one is 1, 2. The reason it's 2 is because my base is 2 from the equation. So I can plot these 2 points on my graph, 0, 1, 1, 2, and then I can draw my curve. Now exponential curves always start slow and then take off high fast. So it's called a slow rising curve. Now since I have 0 here as my k value, that means my asymptote line will be drawn in at y equals 0. That's the blue line that you see dotted right through here. So my curve comes close to that but does not touch. My domain is always all reals, and my range is y greater than 0. My range value is going to be the same number as I use as my asymptote. So if my k value is 0, that means my domain is above 0 and my asymptote line is at 0. The second one, y equals 3 to the x. Since I'm using 3 as my base, then my second go-to point is 1, 3. We could put our 2 dots on here, 0, 1, 1, 3. Since I do not have a k value in the back, that means my my range will be all y values greater than 0. My asymptote line will be at 0. That's the dotted line going this way, the don't touch me line. And then you can draw your slow rising curve. The other one I have on this slide, y equals 4 to the x, follows the same pattern as what we have on the others. Our go-to points are 0, 1, 1, 4. Since my base value is 4, that's why I use the 1, 4 spot. Again, we do not have a k value, which means my range is all y values greater than 0, and my asymptote line again is at y equals 0. And then the rest of the curve, slow rising, pick up your 2 dots, and then take off high. Now, this next slide, I have one shift in here, and that's just this one right here. So our equation is y equals 4 raised to the x plus 1. There's no a value in the front, and there's no k value in the back. You should be able to answer the range question and the asymptote line automatically without even looking at your picture, knowing what that k value is in the back. Since I have a plus 0, that means my range is y greater than 0, and my asymptote line is y equals 0. So I drew in the blue dotted line to represent the asymptote line. Since we are in 4 as our base, my go-to points are 0, 1, 1, 4, and then we shift. Now remember, anything attached with the x, we do the opposite of what it says. It says plus 1, I have to subtract 1. So from the x-coordinate of 0, I will subtract 1. That gives me negative 1. And then down here, 1 subtract 1 gives me 0. So the new x coordinates for my go-to points become negative 1 here, 0 here. The y value, since I do not have an a term to multiply by, and I have nothing to add in for my k value, my y term stays as 1, my y term of 4 stays as 4, and those become my new dots. You can go ahead and plot negative 1, 1, 0, 4, and connect them with a slow rising curve. And remember, on this left-hand side, do not touch your asymptote line. That's the guide that you come close to, but do not touch. Your next example, I'm adding in another shift. Y equals 4 raised to the x plus 1, and then plus 2. So the first thing we'll have is an x shift. Again, it says x plus 1 on the top, which means we will be doing minus 1 to the x-coordinate. We do not have an a term, so I don't multiply my y-coordinate by anything, and I will add 2 to the y value. So let's start with the x's. First of all, my go-to points are 0, 1, 1, 4. 4 because we are in base 4. To the x-coordinate, I will be subtracting 1. 0 subtract 1 is negative 1. 1 subtract 1 is 0. Now I move to the y term. Nothing to multiply by since I do not have an a term, which means all I do is add 2 to the y value. 1 plus 2 is 3. 4 plus 2 is 6. And those are the points that I will plot. Negative 1, 3 is here. 0, 6. And then we need our asymptote line. We've got the number plus 2 in the back. Follow the dotted line here. Plus 2 in the back means that your asymptote line is the horizontal at y equals 2. And my range, same value, my range will be all y numbers greater than 2. So the asymptote line is dotted in, and then we can connect coming close on the left, and then take off high going upwards. Domain again, all reals every time on the exponential growth graph. Now this next one has all 3 shifts going on. Y equals 4 times 2 raised to the x minus 1, subtract 3. So we start with our go-to points, 0, 1, 1, 2. Why the 2? Because I'm in base 2. Now how do we shift? Look at the x-coordinate first. It says x minus 1. We have to do the opposite, plus 1. Take each x-coordinate and add 1. 0 plus 1 is 1. 1 plus 1, 2. Now move to the y value. I've got a stretch number, so the second thing I do is multiply the y value by that stretch number of 4. Multiply by 4. 1 times 4 is 4. 2 times 4 takes me to 8. And the last thing I do is look in the back and deal with my k value. It says minus 3. I subtract 3. 4 subtract 3 is 1. 8 subtract 3 is 5. And those are my final 2 go-to points. So we can go to our graph, plot the points 1, 1, 2, 5. The number in the back of our equation, let me slide down again, number in the back of our equation was -3, which means that value is my asymptote line, so I draw in a dotted asymptote line at -3. My curve will come close to that on the left, pick up your 2 dots, and then take off going upwards. Range, y is greater than that same number, greater than -3. Asymptote line, y equals -3. Domain, all reals, every time. This is one of your homework questions. This is number 16, so if you want to look at your sheet that you're going to be putting your homework on, you can do this one right in your homework. 5 times 4 raised to the x plus 2. Your go-to points, 0, 1 all the time, 1 comma, what? What's going in there? What base are we in? Hopefully you can recognize 4. So it'll be 0, 1, 1, 4. And now we do our shifting. Do you have anything next to the x? No, your x value will not change at all. Now move to the y value. We do have a multiplier of 5. So take your y number of 1, multiply by 5. We've got 0, 5. 4 times 5, 20. Now look in the back. We do have a k value in the back. I have to add 2 more onto my y value. 5 plus 2 takes me to 7. 20 plus 2 takes me to 22. And those are the dots that we can then put on our graph. Let's do the domain and range question real quick. Domain, every time, all reals. The range, look at the k value. Range will be greater than 2. And your asymptote line, same value, y equals 2. So you can go to your graph, dot in your asymptote line right away. That's your boundary line. You cannot come close to that line. You can't cross that line, but you can come close. We know our points are at 0, 7. And the other one is at 122. So for me, that's way up here someplace. I can't even graph it. And then I can go ahead and connect. Coming close on the left, pick up your 2 dots, and then take off. Word problems. But before we do word problems, let me tell you a story about my little Hannah. So you know we have this cabin in Prairie du Chien, and one time when Hannah was little, she was playing, and all of a sudden we heard this big scream going on, so we went looking for Hannah. She was underneath the steps that lead up to our cabin, and she was waving her hands around the air like she had just walked through a big spider web, except it wasn't really a spider web, it was an old fishing line, and she was waving her hands so much that the fishing line went across her face, and unfortunately attached to the fishing line was an old fish hook with 3 barbs in it, and she grabbed the line and swung the barbs right through her earlobe. Well, if you know what barbs look like, they have a really sharp point on them. Once it goes through something, you can't pull it back out again because it rips it right out. So little old Hannah, at the age of probably 4, we had to take her to the emergency room, and they had to cut the barb off and then pull the hook back out of her ear. So that's Hannah's little oopsie mishap at the cabin when she was about 4 years old. Okay, word problems. When you deal with word problems and exponential growth, your basic equation, a times b to the x, now is going to change a little bit. We're going to replace the letter b with the value of 1 plus r. R refers to a rate that something is growing by. We still have a in the front. That's going to talk about the initial value in the word problem. And then x is typically going to refer to time. How much time is going to go by where we're looking at some type of growth. Probably one of the most common growth equations or growth samples is putting money in the bank and let it grow interest for you. So that's a simple example of what we're going to do. So the key that people need to remember is that when we plug this b value in as 1 plus the rate, you must always change your rate from its percent form. Say you're getting 7% interest. You need to make sure you change that into a decimal. Move your point 2 spots, and that's probably the one place where people make mistakes. is you must change your percent back into a decimal. Okay, so here's a sample. In 1996, there were 2,573 computer viruses. The amount of viruses grows by 92% each year. Write the model for this situation. Well, first off, you should right away change 92% into its decimal form. Move your point 2 spots, 0.92. Okay, so now we're going to write a model. We need to write y equals a times 1 plus r and then raised to the x. A is our start number. We started with 2,573 viruses. Y equals 2,573. Inside the parenthesis now is what's called our growth factor. 1 plus the rate, 1 plus 0.92, and then raised to the x. We can go ahead and combine. There's your official model, 1.92 raised to the x. Next part of a question. How many viruses were there in 2003? Well, this thing started in 1996. We're now looking at the year 2003. How much time went by? 7 years. So I want to know how many viruses there were 7 years later. Where are we going to put the value 7? Right here in the x position. X referring to time. So what you're typing in on your calculator then will be 2,573 parenthesis 1 or times by, either way, 1.92 raised to the 7. And then your calculator will hopefully come up with that value. And since we know we can't have 0.7 of a virus, you can go ahead and round those, but you never round up when you're dealing with people or money or something like the virus. So you're just going to leave that at 247,484 viruses. You can put the squiggly approximate signs to represent that. That would be fine. Banking questions. When you're dealing with banking questions, we're going to change our growth model just one more time. And instead of seeing A1 plus B raised to the t, we're now changing that b value into something that will reference money. So it now looks like this. P parenthesis 1 plus r over n, and then raised to the nt. Now you need to know what each of those values stands for. This is a perfect equation to put into your cheat sheet for your final exam. So dig that cheat sheet out again. A is the ending amount of money. How much are we going to have when we're all done? P is what you're going to put in the bank to start with. Maybe you're going to deposit $500 that Grandma gave you or something. R is the rate that the bank will give you. Again, always change that percent into a decimal, so move your point 2 spots. N is the compounding time. If you ever talk to your banker, you want to find out how your bank compounds your money. These are the typical ones. They could compound monthly, which means it's going to happen 12 times a year. It might be quarterly. Typical investments, banking investments, will compound your money quarterly. If you can find a bank that compounds your money daily, that's even better yet. At the end of every day, you're going to get some more interest. And then the other one would be compound annually, which means it's going to take till the very end of the year before they give you any interest. The more your bank compounds the money for you, the better it is for you. All right, so here's an example. I deposit $4,000 in an account that pays 2.92% interest compounded quarterly. Write the model. All right, so let's do one thing at a time. 2.92%. I have to change that into a decimal. Move your point 2 spots. 0.292. Compound quarterly. If you look at your chart, quarterly means 4 times. So when I use my formula, I'm going to have to put the compounding time twice. I'm going to have to put the 4 in down here and the 4 in up here. All right, so let's put it all together to write the model. 4,000 parenthesis 1 plus 0.092 divided by 4, and then close the parenthesis, raised to the 4t. Now here's a mistake that people will make. Please be sure you divide by 4 first before you add in the 1. Too often people want to do 1 plus 0.092 and get 1.0292 and then divide by 4. No, you can't do that. order of operations, you need to divide first. So on your calculator, get this number first, then you can add in your 1, 0.0073. Then add in the 1. 4,000 times 1.0073 raised to the 4t. And then they're asking us how much will I have after 5 years. So then I can put in my 5 in place of t, 20. And then you can just punch it in your calculator. And it will be 46.26 and 33 cents. Again, don't round your money. If that said .337, banks are never going to give you the benefit of the extra penny. So always round your money down, don't round up. I believe that was it. All right, so a couple formulas you need to get into your notebook and especially onto your cheat sheet. Compounding money. Definitely put a compound question in there. Exponential growth, and these will be for things that are not compounding money, like computer viruses, population of a town could be growing. You're going to want to use this formula right here. So make sure that is in on your cheat sheet as well. And then, obviously, our basic, this guy right here. Our basic exponential growth function written in its vertex form with the shifts A, H, and K. All right, now you go to Skyward. Open up your Skyward online attachment quiz, do your 3-question quiz. All right, we'll see you tomorrow.